What if I told you there's a planet out there so impossibly large, so mind-bendingly massive, that it shouldn't even exist? A world so bloated and stretched that it's literally tearing itself apart. A gas giant so close to its star that its atmosphere is being ripped away into space, trailing behind it like a cosmic tail millions of kilometers long. This isn't science fiction, this is real. And it's called ROXS 42BB. Welcome back to Beyond Space. Where we explore the universe one mind-blowing idea at a time. Today, we're diving into one of the most extreme discoveries in modern astronomy, the largest planet ever found in our universe. A world that challenges everything we thought we knew about how planets form, how big they can grow, and what happens when you push the laws of physics to their absolute breaking point. So buckle up, because we're about to journey to the edge of planetary possibility. Let's start with a number that will put everything into perspective. Jupiter, the king of our solar system, is enormous. It's so large that you could fit 1,300 Earths inside it. Its mass is more than twice that of all the other planets in our solar system combined. When we look up at Jupiter through a telescope, we're staring at a giant that dominates our cosmic neighborhood. But Jupiter is nothing compared to what's out there. The largest planet ever discovered is a monster called HATP 67b, and it's located about 1,200 light-years away from Earth in the constellation Hercules. This planet is so large that its radius is more than twice that of Jupiter. Imagine that for a moment. Twice the size of the largest planet in our solar system. But here's where it gets truly bizarre. Despite being twice Jupiter's size, HATP 67bi has only about a third of Jupiter's mass. How is that possible? The answer lies in one word: puffiness. HATP 67b is what astronomers call a puffy planet, or a hot Jupiter on steroids. It's a gas giant that's been inflated to such an extreme degree that its density is less than that of styrofoam. We're talking about a planet with a density of just 0.05 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Cork has a density of about 0.25 grams per cubic centimeter. This planet is lighter than cork, lighter than balsa wood. If you could somehow place HATP 67b in a cosmic ocean, it would float like a beach ball. But why? What force could inflate a planet to such impossible proportions? To understand HATP 67b, we need to talk about hot Jupiters. Hot Jupiters are gas giants that orbit incredibly close to their parent stars, often closer than Mercury orbits our Sun. These planets complete their orbits in just a few days, sometimes even hours. And because they're so close to their stars, they're subjected to intense stellar radiation and heat. HATP 67b orbits its star once every 4.8 days. That's fast. But what makes this planet truly extreme is the amount of energy it receives from its star. The stellar radiation bombarding HATP 67b is so intense that it heats the planet's atmosphere to temperatures exceeding 2,000 degrees Celsius. Now, when you heat a gas, it expands. That's basic physics. But on HATP 67b, this expansion is taken to an extreme we've never seen before. The intense heat from the star doesn't just warm the outer layers of the atmosphere. It penetrates deep into the planet, heating the interior and causing the entire world to swell like a balloon. The atmospheric gases become so energized that they push outward with tremendous force, inflating the planet to sizes that seem to defy the laws of gravity. But there's more to the story. Scientists believe that the inflation of hot Jupiters like HATP 67b isn't just about heat. There are likely other mechanisms at play, mechanisms we're only beginning to understand. One theory suggests that the intense magnetic fields generated by the planet's rapid rotation and proximity to its star create electrical currents in the planet's interior. These currents generate additional heat through a process called ohmic dissipation, further inflating the planet from within. Another theory proposes that tidal forces between the planet and its star create friction in the planet's interior, generating heat and contributing to the inflation. The truth is, we don't fully understand why planets like HATP 67b grow so large. and that's what makes them so fascinating. These worlds are pushing the boundaries of planetary science, forcing us to rethink our models and theories. But HATP 67b isn't alone. There's an entire class of these puffy planets out there, each one more extreme than the last. Take WASP 107b for example. This planet has a radius about 94% that of Jupiter, but a mass only about 12% that of Jupiter. Its density is so low that scientists describe it as having a cotton candy consistency. Or consider KELT 9b, the hottest planet ever discovered. With daytime temperatures reaching 4,300 degrees Celsius, KELT 9b is hotter than some stars. At these temperatures, molecules in the atmosphere break apart into individual atoms. Iron and titanium vaporize and rain down from the sky. The planet is so hot that it's literally evaporating, losing mass at a rate of about 10,000 to 100,000 tons per second. Then there's HD 209458b, nicknamed Osiris, which was one of the first exoplanets discovered to have an evaporating atmosphere. Astronomers detected a massive cloud of hydrogen escaping from the planet, forming a tail that stretches for millions of kilometers. These planets are dying. They're being torn apart by the very stars that gave birth to them. And that raises a profound question. How did these planets end up so close to their stars in the first place? In our solar system, the gas giants are far from the Sun. Jupiter orbits at a distance of about 778 million kilometers. Saturn is even farther out at 1.4 billion kilometers. This makes sense because gas giants form in the cold outer regions of a solar system, where ice and gas are abundant. But hot Jupiters orbit their stars at distances of just a few million kilometers. They couldn't have formed there. It's simply too hot for gas giants to coalesce so close to a star. So what happened? The answer is planetary migration. After a planet forms in the outer regions of a solar system, gravitational interactions with other planets, with the protoplanetary disk of gas and dust, or with the star itself, can cause the planet's orbit to change. Over millions of years, a gas giant can spiral inward, migrating closer and closer to its star. But this migration is a dangerous journey. As the planet moves inward, it enters regions of intense heat and radiation. Its atmosphere begins to expand. If the planet migrates too close, the star's gravity can begin to tear it apart through tidal forces. The planet becomes stretched and deformed, with one side perpetually facing the star and the other side in eternal darkness. Eventually, the planet reaches a point of no return. The stellar radiation is so intense that the atmosphere begins to evaporate. The planet starts losing mass, bleeding its gases into space. This is the fate of many hot Jupiters. They're temporary phenomena, cosmic fireworks that burn bright and fast before fading away. HAT P67b is in this precarious state right now. Its extreme puffiness suggests that it's losing its battle with its star. The planet is so inflated that its gravity can barely hold on to its outer atmosphere. It's a world on the edge of disintegration. Let's put the scale of these planets into perspective with a thought experiment. Imagine you're standing on Earth, looking up at the sky. Now imagine that Jupiter suddenly appeared in place of our moon. Jupiter is enormous, right? It would dominate the entire sky, stretching from horizon to horizon. It would be a breathtaking, terrifying sight. Now replace Jupiter with HATP 67b. HAT P67b would appear even larger, filling an even greater portion of the sky. But here's the strange part. If you could somehow stand on HAT P67b, you would barely feel any gravity. Despite the planet's enormous size, its low density means its surface gravity is only about 20% that of Earth's. You could jump several meters into the air with ease. You would feel almost weightless, floating across the surface of a world larger than Jupiter. But of course, you couldn't actually stand on HAT P67b. It's a gas giant with no solid surface. If you tried to descend into the planet, you would simply fall through layer after layer of increasingly dense gas, the pressure and temperature rising with each kilometer, until you were crushed and incinerated long before reaching whatever core might exist at the center. And that's assuming the intense radiation from the nearby star didn't kill you first. So what do these extreme worlds teach us about planets in general? First, they show us that planetary systems are far more diverse than we ever imagined. Before we discovered exoplanets, we assumed that all solar systems looked more or less like ours. rocky planets close to the star, gas giants farther out, everything in neat, stable orbits. But the universe doesn't follow our expectations. We've discovered planets orbiting binary star systems, planets with orbits so eccentric they swing from scorching heat to freezing cold, planets made of diamond, planets covered in global oceans, and planets like HATP 67b that are so extreme they challenge our understanding of physics. Second, these puffy planets reveal the fragility of worlds. We tend to think of planets as eternal, unchanging objects, but planets are dynamic, evolving systems. They're born, they change, and they die. HATP 67b is dying. In astronomical terms, it won't be around for long. Over the next few million years, it will continue to lose mass, its atmosphere stripped away by stellar winds and radiation. Eventually, all that will remain might be a small, dense core, a remnant of what was once the largest planet we've ever discovered. Third, studying these extreme planets helps us understand our own solar system. Why did Jupiter stay far from the Sun? What prevented it from migrating inward and becoming a hot Jupiter? The answer likely lies in the gravitational influence of Saturn and the specific conditions of our solar system's formation. We're lucky. If Jupiter had migrated inward billions of years ago, it might have disrupted the orbits of the inner rocky planets, including Earth. Life as we know it might never have emerged. Let's talk about the discovery process for a moment, because finding these planets is no easy feat. HATP 67b was discovered using a method called the transit method. This is one of the most successful techniques for finding exoplanets. Here's how it works. When a planet passes in front of its star, from our perspective, it blocks a tiny fraction of the star's light. By monitoring the brightness of stars over time, astronomers can detect these periodic dips in brightness and infer the presence of a planet. The amount of light blocked tells us the size of the planet. The frequency of the dips tells us the planet's orbital period. And by analyzing the starlight that passes through the planet's atmosphere during a transit, we can even determine the composition of the atmosphere. This is how we know that HATP 67b has such a low density. The depth of the transit tells us the planet's radius, while other measurements give us its mass. Divide mass by volume and you get density. But here's the remarkable part. We're detecting these dips in brightness from planets that are hundreds or thousands of light years away. We're talking about changes in brightness of less than 1%, sometimes less than 0.1%. It's like trying to detect the dimming of a car's headlight when a fly passes in front of it, from a distance of several kilometers. And yet, we're doing it. We're finding these planets, studying them, and learning their secrets. Now you might be wondering, could there be even larger planets out there? Planets that make HATP 67b look small by comparison? The answer is complicated. There's a theoretical upper limit to how large a planet can be. As you add more and more mass to a gas giant, the planet's gravity increases, compressing the interior and actually making the planet smaller, not larger. This is why Jupiter and Saturn, despite Saturn having about a third of Jupiter's mass, are roughly similar in size. If you keep adding mass, eventually you reach a point where the core becomes so hot and dense that nuclear fusion begins. At that point, you no longer have a planet, you have a star. The boundary between planet and star is defined by an object called a brown dwarf. Brown dwarfs are sometimes called failed stars because they're too massive to be planets, but not massive enough to sustain hydrogen fusion like true stars. The most massive planets we've discovered are right at this boundary, with masses about 13 times that of Jupiter. Beyond that, we're in brown dwarf territory. But when it comes to size, not mass, planets like HATP 67b are likely near the upper limit. Their extreme puffiness is a result of very specific conditions: intense stellar radiation, low mass, and likely some additional heating mechanisms we don't fully understand. There could be other puffy planets out there that are slightly larger, but we're probably not going to find a planet twice the size of HATP 67b. At some point, the laws of physics say no. Let's zoom out for a moment and consider what all of this means for the search for life in the universe. Hot Jupiters like HATP 67b are obviously not habitable. They're far too hot, far too hostile, far too extreme for life as we know it. But their existence tells us something important about planetary systems. In systems with hot Jupiters, the migration of these giant planets inward likely disrupted the formation of smaller, rocky planets in the habitable zone. When a gas giant migrates, it can scatter or eject other planets, leaving behind a chaotic, unstable system. This means that systems with hot Jupiters are probably poor candidates for hosting Earth-like worlds. On the other hand, the fact that we find hot Jupiters in a relatively small percentage of star systems suggests that most planetary systems don't experience this kind of dramatic migration. Most systems might be more like ours, with gas giants staying in the outer regions and rocky planets forming closer to the star. This is good news for the search for life. But there's another intriguing possibility. Some hot Jupiters might have moons. And if those moons are large enough and have the right conditions, they could potentially be habitable, even in a system with an extreme planet like HATP 67b. It's a long shot, but it's a reminder that the universe is full of possibilities we haven't even begun to explore. As we wrap up, I want you to think about what we've covered today. We've journeyed to a world 1,200 light-years from Earth, a planet so large and so puffy that it floats like styrofoam, a world being torn apart by its own star. We've explored the physics of planetary inflation, the mystery of planetary migration, and the fragility of worlds on the edge of destruction. We've seen that planets are not static, eternal objects, but dynamic, evolving systems shaped by forces we're only beginning to understand. And we've glimpsed the incredible diversity of the universe, a cosmos filled with worlds beyond our wildest imagination. HATP 67b is a reminder that the universe is stranger, more beautiful, and more extreme than we ever thought possible. It's a reminder that there are planets out there that challenge our theories, expand our knowledge, and inspire our sense of wonder. Every discovery like this brings us one step closer to understanding our place in the cosmos. Every new planet we find, no matter how extreme, teaches us something about how worlds form, how they evolve, and how they die. And perhaps most importantly, discoveries like HATP 67b remind us how special our own planet is. Earth is not the largest world, not the most extreme, not the most dramatic. But it's stable, it's habitable, and it's home to the only life we know of in the entire universe. For now, at least. Because out there, orbiting distant stars, there are billions of planets waiting to be discovered. Some will be small and rocky like Earth, others will be massive and puffy like HATP 67b, and some will be unlike anything we've ever imagined. The universe is vast, the possibilities are endless, and we're only just beginning to explore. Thanks for watching. If you enjoyed this deep dive into the largest planet ever discovered, make sure to hit that like button and subscribe for more cosmic content. Drop a comment below and let me know. What's the most extreme exoplanet you've heard of? What discovery do you want us to cover next? Until next time, keep looking up. The universe is waiting.